Math starts by defining numbers and values. And these are the symbols that we use in standard mathematics. And they just represent definite numbers of things. So this represents one thing. This represents two things, so on and so forth. And we use a grand total of 9 values, with this 0 being a placeholder that represents nothing. So we have all these symbols, but they kind of limit us. We don't want to create infinite unique symbols for an infinite number of numbers. So what we do is we create base systems. We use base 10, which means that once we hit 9, we use 0 in the placeholder of the spot and place the 1 here at a new digit. And this is interesting because you can actually do this with any number. Binary is really one of the only other systems that we use, and computers use it. And as you can see, we have the same principle. We will never exceed a symbol over 1, which means that once we hit the cap here, we move to a new digit. Then we continue rising the numbers on the left, and we move to a new digit, and so on and so forth. And the reality is that you can repeat this with any, cap. So here we use our next place here to represent 4, which means that when we reach 20, it's equals 8, because this 2 here represents 2 4s. This is so, yeah, and that's the principle that we need to understand for base 10. Base 10 feels the most intuitive to us, and it's the one that we use because 10 is a very pretty number. So this is 10 ones, this is 10 tens, this is 10 hundreds, but it's 100 tens and 1,000 ones. And maybe this makes sense to us because 10 just happens to be the point at which we run out of standard symbols. And finally, we should establish that these are constant, they are definite. This symbol here always corresponds to 1. This symbol here always corresponds to 4. And that's really the basis of counting and mathematics. And it's just a way to represent quantities through symbols. From there, we can arrange them in a sequence, and we can count up things. Now we need to discuss the in-betweens though, because if this is 1, then what is this? It can totally exist, we just need to be able to define it. And that's where decimals come in. Yes, as our values ascend, we can go into extra digit spaces in order to represent higher values. But we can also go into smaller digits called decimals, separated by a decimal point to define where the ones spot is. And this is how we define numbers smaller than 1. Again, following the base 10 system. Tenths, 10 of these makes a 1. 10 hundredths makes a tenth. We can now apply this to our geometric model, and we can see that if this is equal to 1, we can split it into 10 tenths. This is half of that, which would be 5 of these tenths. Meaning that our corresponding value would be 0.5. If we added a 1 to this, we would get a 1.5. You can extend this into as many decimal places as you want. And you can, of course, do the same thing on a larger scale with the larger places. At the start of this, we established that these symbols have definite values, but they're not the only ones to have definite values. Sometimes we use non-numbers to represent numbers. And yeah, we can use these non-number values to represent these values. Why wouldn't we just write these numbers, you ask? Well, they're actually called irrational numbers. These decimal places go on forever, and so it's much easier to write this little symbol or this little symbol than these entire sequences. Now, these do have very useful purposes in later math and are derived from very interesting things, but that is for a future video. I'm gonna get into basic operations and stuff next time, so that should be fun.